All right, so in Unit 8, we were calling this Unit 8c. This is technically the second and last lesson to 8c. It's double angles. So if you take a look at the first slide, if I turn this on, right, what we're going to do is if I add two angles together that are the same, so instead of splitting them into two different denominators of 12, but it turns out they are the same, we get this 2 sine u cosine u is the definition of 2u. That's why it's called the double angle, because you're taking an angle, multiplying it by 2. You don't need to know all of this. Hey, I got it. I'm here. Oh, okay. Thanks. Yep, you're good. Okay, so we could do the same thing with cosine of 2u and tangent of 2u. Right? For the sake of time, the fact that we are at the end of the course, etc., you can do that. You can pause this and try to do it on your own. Okay, so the first formula that we have, which you can't see very well, is that the sine of 2u is going to be 2 sine u cosine u. You will get these formulas, just like you got the sum and difference formulas of sine, cosine, and tangent. So the double angle, we know it's a double because this is multiplying by 2. For sine, here's your formula. Cosine of 2u is going to give you this final formula right here. This option or this option. So you have 3 choices that you can use based on the information you are given to calculate the sine of, I'm sorry, not the sine, but the cosine of 2u. So blue formula, 3 red formulas, and then in tangent we have a purplish formula. Tangent of 2u is equal to this. So these are the new formulas that you're given, that we're going to use today, and just like the last section, we're just going to plug them in. So write down the blue formula, the red formulas, and the purplish, please. I guess I could just say purple. Good? All right, so that's the whole lesson. Yeah.
What does that mean?
What is what?
Like all of it. What does it mean?
What do you think it means?
I don't know.
Really? I'm going to have to edit this video now because you asked me that question. Here I am sitting here thinking you know how to do it all.
Oh, you could just cut it at the end right after you said.
Yeah, I'll cut it. I'll take the middle chunk out.
So then, like, the people that watch it will not have an explanation for themselves.
Oh, so you do know how to do it?
No, like, I was waiting on your response, and then they
You were helping out imaginary people that might watch this in the future?
I'm helping out the next generation. Well, next year.
Okay, all right. Turn in your notes to the last section where the formulas are. In each, like, quarter of a page, third of a page, there's a formula. Right?
The last one. The last one we did?
Yeah, like the last one. So when I started that lesson, I explained to you that these are the formulas to calculate non-unit circle values, which you can derive by adding and subtracting unit circle values. Right? The new formulas are also a means to calculate non-unit circle values, but rather than adding, subtracting, and that's it, of 2 unit circle values, we're going to multiply unit circle value times 2, or non-unit circle value times 2. Hence the name double angle. Does that make sense?
Yes.
So now you got it, connection made. It's just another formula that allows us to calculate without a calculator actual values. So if we look at our first example, maybe this would be a better way to explain this. Okay, ready? We're now going to do example 1. in example 1, we're going to find the sine of 2 theta. So like the directions are to find the sine of 2 theta when you were only given information about theta. This is obviously a non-unit circle value, right? And remember, theta is the angle. We don't know the angle, so we're going to have to do something about that. So anytime I give you a statement like cosine theta equals root 7 over 4, not a unit circle value, and I give you restrictions, what should your next inclination be? Draw a triangle in quadrant 4. Okay? So we can go ahead, we can draw a quadrant for reference triangle. Remember, these are still reference triangles. So I'm going to come down, I'm going to come up. Here's my theta prime. Cosine is a over h. So this is going to be root 7. This is going to be 4. Is the opposite side positive or negative? Negative. So 7, 16 minus 7 is what? 9, square root of 9 is 3. So my opposite side is 3. Isn't it funny how you can do Pythagorean theorem in your head now, even for these weird ones? Yeah. Most of you are there. Right? So from that, if I want to find the sine, what's the double sine formula say? Double sine. Sine 2 theta is equal to 2 sine theta cosine theta? Like that? Okay. So now I just plug in. I go over to my reference triangle and I say 2 times, what is the sine of the theta prime in this case? Negative 3 over 4. And what is the cosine? Root 7 over 4. Then I just have to do my legal algebra to come up with my answer. Right, so I would end up with negative 6 root 7, all of which is over 16, and then reduce. Ooh, those look pretty easy, right? Yep.
That's the final answer.
Yeah. Use the formula. Figure out how you can take the rest of the given information located over here in order to generate the sine and the cosine you need based on the formula. Come up with your answer. Use legal algebra. Reduce your fractions. Have fun with roots, and you're done.
So what are the other formulas that I'll have the list, or is that just getting to?
Okay, so let's talk about the list. All right, so in example 2, we're talking about tangent of 2x. How many formulas are there for tangent of 2x? How many did I give you? For tangent 2x? Didn't I only give you one, the very last one?
Yeah.
Right, that's the last one, that's the final one. The rest was us deriving that, okay? So this only has one formula to choose from, and example 1 only has one formula to choose from. If you look at the one that you're asking me about, which is cosine, correct? You have 3 choices. Those 3 choices were derived by substituting in a Pythagorean identity to come up with other ones. So you can derive cosine of 2u from either sine squared or cosine squared or both of them. Does that make sense? You can pick which one you need based on what you were given, which is the ultimate math experience. So if I look at example 2, I only have one formula. Again, I've got this same idea of setting up a triangle. Now, this is something that's going to start to happen more and more frequently. Do you see how the cosine of x equals plus or minus 12 over 13? Okay, look at your restrictions. What quadrant should I be drawing my reference triangle in? 2 it is. Okay, 2. All right. Is tangent positive or negative? Is tangent positive or negative in quadrant 2? Negative. So I'm going to have to know that this is negative, this is positive, and use the signs based on the triangle. It's not meant to trick you. It's not meant to do anything else. It's a very kind of just make sure that you're using the signs of the correct reference triangle based on the restrictions. Alright, so like I could give you cosine x equals plus or minus 12 over 13. I could give you these restrictions for a problem, but I could give you different restrictions for a different problem. But the given information could be the same. The plus or minus is dependent on the reference triangle. So if I set this up, cosine is adjacent over hypotenuse. This is a special right triangle. What is the opposite side? 5. So we're recognizing 5, 12, 13. 3, 4, 5. 24, 25, what's that one? 13. All right, so does anyone have a question about blue triangle on the board? Anybody? Theta prime is here. What's the formula for tangent 2x? Tangent of 2x is equal to, read it off. 2 tangent, okay, so I'm going to use x, because I used x over what? Okay, so let's go ahead and put this in. 2 times the tangent of x is what? 5 over negative 12? Over 1 minus 5 over negative 12 squared. All right, so now we're going to really jump into some complex fractions. Up top, I'm going to get 10 over negative 12. Does that reduce? Yes. However, my only caveat to reducing right now is the fact that if you start to make this smaller, notice this is going to go up to 144. You're going to have to think a lot harder probably for your LCD. So it's okay if you don't reduce from the beginning. So this is my top. In my bottom, I'm going to get 1 minus 25 over 144. Both of these are positive because when you square the quantity, the signs disappear. Disappear, wrong word, that sounds like magic. Cancel. So when I look at that fraction, do you see it as having 3 different components? The fraction up top, the 1, and the 144? What's my ultimate LCD? Ultimate LCD? So I'm going to do 144 up here and 144 down here. Ultimate LCD fractions. So this looks like negative 120 over 144 minus 25. How much is that? 119 maybe? Somebody have a calculator? Negative 120 over 119. Answer. So theoretically, once you made the connection, can you see it's just an extension of the same lesson, just more formulas? And these are actually easier formulas, I think. Yes.
So formulas are provided, so all we have to do is just be able to understand it and plug it in.
Be able to understand what you're given, draw the correct triangle in the plane, watching your signs, substitute incorrectly, and then really I'm looking at the algebra of your fractions. This type of complex fraction algebra is all throughout calculus. So just really seeing the terms for what they are, making sure your rules are correct, etc. Somebody had their hand up, yes?
On the open note test on Friday, are we going to be able to use our number?
Whatever is in your notebook. Yeah. Right? Do you have one more example? One more example. Let's take a look. Example 3. All right, so example 3. Do you recognize that this is not what? Does this look like the last one? Like find this, do this? No, this is a trig equation. This is what you had your last test on. Okay, this is a trig equation. So if you remember the trig equation said, is it linear? Is it quadratic? Do you put everything on one side? Do you GCF? Do you do LCD? I mean, there's a lot of different things. Can you split the fraction, et cetera, et cetera? So what makes this tricky, and the reason it's reintroduced, is the fact that if I have cosine 2x, which definition of that do you think, because there's 3 to choose from, Which of the three would be the best to substitute this with? Which one do you think is going to help you the most?
2 cosine squared x minus 1.
2 cosine squared x minus 1. And we choose that because now when I break it down, the plus cosine x equals 0, doesn't that look familiar from the trig equations? If I rewrite the order, 2 cosine squared x plus cosine x minus 1 equals 0. Right, and then from there, what do I do? If I'm solving the trig equation, quadratic, cosine squared, cosine number form, factor. This is on your final, plus 1 minus 1. Alright, then we get down to cosine x equals 1/2, cosine x equals -1. Should give me what? 3 solutions? Where's cosine equal to 1/2? Here and here. X equals what?
Pi over 3.
And 5 pi over 3. And then here, cosine equals -1 at, isn't it just pi?
Yeah.
Right, just pi. So I think the big idea here is the fact that, you know, those definitions you wrote down that you're going to be given, those you can substitute into trig equations just like Pythagorean identities. Good? Yeah.
So if we were to go back to like bulk homeworks we did, would we be able to use these and plug it in and then solve the problem still?
The original ones you had?
Yeah, like
You
older
never
problems we
had, you didn't have any that had a 2 in them.
Oh, okay.
Right? Oh, you're saying if you had like cosine 2x equals like root 2 over 2, the
Yeah,
way
would
you
we
would do
be
the
able to-
multi-revolutions?
Yeah.
You probably could, but I would think,
That would be easier just to.
yeah, like in this case, the idea, whenever we're giving you these equations and the identities, they're puzzles that are meant to be solved by like plugging in and simplifying, you know? And I think the last thing that I can really say about this is, and this is kind of cool that it happens at the end of the unit, when you were younger and you were in math, the fact that you're in honors now, I'm 99.9% sure you all experienced this at some point in your math careers. I don't know when it ended, but do you remember when your teacher would teach you something and you would like get it right away and you would kind of see where she was going, where he was going, and they would put the new type of problem up and your brain automatically went there, like knew how to do it? Do you remember that feeling? And like you were in a class and there were people around you who didn't get it at all? Like you were younger when that happened, most likely. Please tell me you all have that at some point in your life. That's why you're here at honors now. 2 things about school that I just want you to keep in mind. When I said at the beginning of the year, don't ever tell me you're not good in math. Number 1, those of you who, when we got to here and you started, and I just gave you that hint what to do, some of you already were right on this. You had that feeling still, and that's really great. And some of you didn't. You were like, I don't remember any of this. Okay, not a big deal. But that's the joy and excitement, and believe it or not, that's what keeps people involved in academics when they still feel that. And I would say, as your math teacher, someone who's gotten to know you, please choose something to study in college that you feel that way about. That you have an interest, that you can see forward in it, that it excites you, that it gives you that mental, like, stimulation. It doesn't have to be about math, but find something. Don't just go to college to go to college. It's too expensive. Really, truly, that's my big thanks for being in my class speech. And now we're done for today. I'm going to edit all this out, so I don't care. Right? Questions?